Welcome back to Principles of fMRI. In this module, we're going to talk about psychological inference and what kinds of questions we can and can't ask with fMRI. So what can neuroimaging tell us? Well, the news media is full of examples like this one from the New York Times, in which Martin Lindstrom scanned some people with fMRI and claimed that he could measure whether they liked or even loved their iPhones. Here's what he says. Most striking of all was the flurry of activation in the insular cortex of the brain, which is associated with feelings of love and compassion. The subject's brains responded to the sounds of their phone as they would respond to the presence or proximity of a girlfriend, boyfriend, or family member. In short, the subjects didn't demonstrate the classic brain-based signs of addiction. Instead, they loved their iPhones. The question is this something that we can say from the brain? This isn't just in the media. There are many new potential applications emerging, including applications in law, in clinical science, and others. So here, this quote is from a judge, Justice John Kennedy. He says, "Scans can reveal if a person is in pain or mentally competent to stand trial, but not guilt." We'll ask later on in the course if that's true and under what circumstances. When we think about making psychological inferences like these, what we're really doing is we're trying to understand this question. Here's a brain map. This is a typical brain map. What does this map mean? What kinds of psychological functions is this associated with? Well, I've circled in red some key areas that should help you decide. There's the anterior cingulate, the anterior insula, the medial thalamus, S2, which is somatosensory cortex, S1, which is also somatosensory cortex. So I think all these areas are activated by pain. So maybe it's pain. We can look at neurosynth.org, which is a database that now has over 10,000 studies. Each of those blue dots is a point from one study. And we can ask, studies that activate this pattern, things like this, what is it that they tend to talk about in their papers? The top hits for this pattern: noxious, heat, somatosensory, painful, sensation, stimulation, muscle, temperature. So maybe now you're even more confident that it's pain. I would be. But in fact, you'd be wrong. This map comes from a study of romantic rejection. It was published a few years ago in PNAS. So that's the pattern of reverse inference. That's the process of reverse inference. And that's one idea about what can go wrong. Let's go back now and think about, when we do neuroimaging studies, what kinds of questions can we actually ask? And this starting point for this is really a seminal paper by Steve Coslin many years ago called this, "If neuroimaging is the answer, what is the question?" And he basically makes the argument that neuroimaging analogies should be designed to test theories. And so we have to think, what kinds of theories are actually amenable to testing with neuroimaging studies? So a typical result is a statistical map where the colors indicate reliable, non-zero effects. Statistical maps are used for hypothesis tests at each of a number of voxels or regions of the brain. So effectively, the question that we can ask is this brain voxel responding to my task? How about this one, or this region? That's the question we can ask in a very strict statistical sense. And this is the brain mapping approach. So the answer that it provides is a hypothesis test on whether task-brain or brain outcome relationships, whatever I'm testing, is not zero. There are many choices about how to do my tests. On the left here, I can do tests on each voxel in the brain across the entire map. I can define some regions of interest. I've drawn circles around those, so I can test each voxel in a set of regions of interest. I can test each voxel in one region, or I can just average over one or more single regions and test that. And these tests differ a lot in certain ways. They differ in the degree of multiple comparisons correction required. We'll learn about that later. So on the left, you have many, many tests, so you need very stringent evidence. On the right, there's only really one test, and so in one region, so you need less evidence to be able to conclude that this result is significant. And you can test activation, you can test correlation maps, you can test maps of predictive activity or connectivity or other things. But fundamentally, the hypothesis testing framework is the same. We're asking whether there's a non-zero effect. So what's the answer? Given the model assumption, this brain area shows some effect. but that doesn't necessarily provide any information about how big that effect is, about how meaningful it is, or about whether it really explains or predicts a behavior. And so this led Coslin to write some years ago, the demonstration that a particular pattern of brain activity accompanies the performance of particular tasks isn't really very interesting. We can only interpret those data in the context of theories. So this answer is only a good answer if your theory requires that the brain data have something to say about it, or if the brain data can say something about it. So how do we use imaging to address psychological theories? Well, the key is that result, whether the brain activates or not, has to constrain your psychological theory. It has to tell you something that you didn't already know. And to learn something about the mind, we need to demonstrate a concept called reverse inference. I'll explain what that is pretty soon. The first thing to note, though, is that brain mapping doesn't provide reverse inference. It provides something very different, which is called forward inference. So forward inference is, given that I've induced a psychological state, maybe it's pain, then we observe some brain activity. And forward inference concerns the probability of observing that brain activity, whether it's a region or a pattern or whatever, given the fact that I've induced the state. I'm in pain. Reverse inference is in some sense the complement. Can we infer a psychological state given a pattern of brain activity or activity in any particular region or marker? These two things are not the same thing, and they can be very different, both qualitatively and quantitatively. And in fact, there's a name for fallacious reverse inference, for doing a forward inference mapping study, what's active when I'm in pain, and then making the conclusion that those regions must imply that I'm in pain. And that logical fallacy is called affirming the consequent. And here's how it goes. Going back from brain to another simple example. Dogs like ice cream. Mary likes ice cream. Therefore, Mary is a dog. When you frame it that way, you can see it doesn't make sense, right? It's not true. So the logical form here is if P, then Q, Q, and therefore P. So that's the fallacy. We'll call it false reverse inference. So in fact, I can relate forward inverse inference quantitatively using Bayes' rule. So Bayes' rule relates to forward inverse inference, and what it says is that the reverse inference that I care about is the probability of psychology given the brain, and that is related to the base rate, the probability of the psychological state. It's related to the probability of brain activity, the base rate of brain responses of that type, and it's related to the evidence. So here's a work-through example. Does punishing wrongdoers feel good? So the idea of this study here, just to pick out one among many as an example, is that punishing wrongdoers feels good because it activates pleasure centers in the brain. So what did they do? They gave people the opportunity to punish somebody who was a wrongdoer, and what they saw when people were doing that is activation in this brain area right here, which is part of the caudate nucleus. So the forward inference is, if you're punishing wrongdoers, we activate the caudate. The reverse inference is, if you activate the caudate, you must be enjoying. So here's the logical premises of the logical fallacy we talked about earlier applied to this case. So it would go like this. 1, if I'm enjoying something, that's if P, then my caudate is activated, Q. And this can be quantified in terms of sensitivity. What's the probability of observing caudate activity given that I'm enjoying something? Number 2, my caudate is activated, that's Q. And number 3, therefore, am I enjoying? That's the fallacy. And it's only actually true if enjoyment is the only thing that activates the caudate nucleus. And this can be quantified in terms of specificity, which is 1 minus the probability of getting caudate activity if I'm not enjoying. I could be doing anything else. So let's do a little application of Bayes' rule to this particular example scenario. So for reverse inference, what we're interested in is another quantity called the positive predictive value. In this case, the positive predictive value that I'm enjoying something given that I've activated the caudate. So let's work this through. So let's say enjoyment activates the ventral caudate, and the sensitivity is quite high. So the probability of observing that caudate activity given I've enjoyed is 0.9, 90%. So that's the high sensitivity. And let's now look at the specificity. So if I'm not enjoying things seldom activate the caudate. Let's say probability of observing the caudate without enjoyment is 0.4. That's 1 minus the specificity. And let's say the base rate of enjoyment is 10%, 0.1, and that's a prior unenjoyment. Then I can calculate the positive predictive value using Bayes' rule. And you can guess, what do you think it is? Given these numbers, how likely is it that people are really enjoying something if they get activation of the caudate? And here the answer would be 0.2. Not a very compelling number. So this demonstrates how you can get very high sensitivity, 90%, 0.9, and very low positive predictive value, especially if the base rate is low. So the reverse inference take-home is the following. Reverse inference is the practice of treating the brain as a marker for something. Could it be the caudate? It could be any other brain pattern. When people make reverse inferences, they assume that there's high positive predictive value for that marker. This positive predictive value can be calculated, but it requires the assessment of multiple tasks and other states that are potentially confusable with the outcome or task of interest. So this is a process that is often played out across many studies and many conditions, not just one. And for brain activity in a particular region, like the caudate, to have high positive predictive value, it has to respond consistently to the task with high sensitivity, and it must respond only to that task, which is with high specificity. The problem is that that's rarely the case.